we know anytime something goes from a higher energy to a lower energy, that energy difference has to go somewhere. So in some chemical processes, a higher potential energy to a lower potential energy, sometimes that energy is converted into heat energy or kinetic energy. But for electrons, it's usually converted into light energy, right? So we see that with the sun. When the sun shines, it's because there are there are high energy particles on the sun, and they're relaxing down and becoming lower energy particles, and that energy is emitted in the form of light. And we see the same thing when we heat something up, the white hot glow of the metal. We already talked about that. That's because we're exciting these electrons to higher energy levels, and when they relax back down, they release energy. Some of the energy is released in the visible region we can see, some of the energy isn't. So this is for the hydrogen experiment. We just saw this. We just saw the simulation of this. But what we saw was the hydrogen atom with its electron, and that got excited by having another electron come in there and collide with it. So that works. That electron can then, if it's in n equals 1, it can move to n equals 2. And when it does, after it's excited, then when it relaxes and it moves back down, it will release light energy. Right? So only from a higher state to a lower energy state will energy be released. And only if that energy quantity, well, whatever that energy quantity is, it will correspond with a specific wavelength of light. In the colored region, though, we know that that has to be a higher energy down to n equals 2. So another way to excite that electron, though, instead of bombarding it with electrons, would be to connect it to an electricity source or a voltage, and we have that in lamps. So this is, if you have neon lights, you can make helium lights, you can make hydrogen lamps. So each different element has its own energy levels, and so it will emit its own specific color of light when you put it in this lamp. So basically, we're using this voltage to provide the initial energy. That voltage goes into the hydrogen atom and excites its electron or breaks some of its attraction. So we'd have to dial in the voltage just right? We don't want to make it too high, or it'll knock the electron out completely. We don't want to overcome its attraction to the nucleus entirely. We just want to move it up to an n equals 6 or n equals 5, and then have it relax back down to n equals 2. Right? Because that will provide these specific wavelengths from 6 to 2, 5 to 2, 4 to 2, or 3 to 2. And so the main thing here is, well, one nice thing about it is we can create lamps of various colors depending on what element we use and what energy levels are associated with that element. But the main thing this tells us about the behavior of matter is that electrons are quantized. Right? So that's the key thing here. Electrons can only exist at certain energy levels in an atom. If I want to move an electron from one energy level to a higher level, if I don't have that quantity of energy, I can't do it. It can't go part of the way. So the electron will be at a lower energy on its own. Naturally, that's where it naturally sits in the ground state. If I want to move it to a higher energy level, I have to put in that quantity of energy somehow, through an electricity source or light or bombarding with electrons that have that energy already or something like that. Once it has that energy, then it can relax back down. But there are only certain energies it can have because we only see certain energies of light coming out during the relaxation process that occurs after it's excited. Any questions about that? Okay, so here are a bunch of different emission spectra for a bunch of different elements. So let's see about this link. I'm not sure we're going to spend a lot of time on it since it's probably similar to the one we just looked at. So, let's see, maybe that is the one we just looked at. Oh, we already looked at this one. So that one we don't need to worry about. But basically what this slide is telling you is that depending on the element, each element has its own degree of attraction between its nucleus and its electrons, right? Each element has a different number of protons. So each element has its own attraction associated with those protons to its electrons, and the energy levels that those electrons experience in that atom will be different from the electrons in other atoms. But all the elements have this quantum behavior for the electrons. They all have only certain energy levels where the electrons can be. The electron can't just be anywhere. It has to be in one of these levels. It can transition from level to level depending on the energy associated, but it has to be in one of the levels. So based on this behavior, Niels Bohr, a brilliant guy, came along and hypothesized that, well, it became more of a theory, but his idea was that since we know there are only certain levels, let's call those levels quantum levels, because there are certain quantities of energy associated with the different levels, and the electrons have to be in those levels. They can't just be anywhere. And so he came up with a model for the atom that allows the electrons to have this quantum or stepwise behavior. And well, there's no picture of that. So it's a pretty basic picture. That actually, let's go to this here. This is kind of an interesting simulation that helps illustrate that picture. So there's a billiard ball model for the atom. So this was like a really early model before Niels Bohr. So if we shine light at that, so white light is basically photons at different wavelengths. So the different colors here are just meant to show the different wavelengths. So if the atom were a billiard ball, it would just reflect the light. But that's not how atoms behave, right? We know they don't just reflect all wavelengths of light. So that model is no good. This is an interesting depiction of the plum pudding model. So we know the plum pudding model is no good because, let's make this a little faster. Because of the Rutherford Gold experiment. That experiment tells us that the protons and neutrons are in the nucleus and the electrons are not, right? The electrons are somewhere around the nucleus. So the plum pudding model just would say that the electron can bounce around anywhere in the atom, but that's not correct. So we could think of it as a solar system model. I don't understand this one at all and why it's exploding, so we'll just skip that one. So this is Niels Bohr's model. Okay, so Bohr said that the electron is kind of like in an orbit or a specific energy level. So this model came from the experiment we just saw, where we know the electron can't just be anywhere. The electron normally is close to the nucleus, but if it gets excited and it absorbs energy, it will move to somewhere further out from the nucleus into a different energy level. The electron cannot be in between this energy, between that energy level and that energy level. It has to be in one of those energy levels. It can't just be anywhere. That was a pretty good model. That's basically the Niels Bohr model, so we'll come back and talk about the rest of these here in a minute. And it's based on the idea that the electron can't just be anywhere. It has to be in one of these energy levels. And that matched up with these early experiments. And Balmer was the one who characterized the specific energies associated with the transitions that give the colored light for hydrogen. So this is a formula. We just saw the first part of this formula. But what the addition to this formula shows is that I could pick any two energy levels and put in their quantum numbers and calculate the energy associated with that. Right? So just to point out, energy level 1, this is the ground state. That's where the electrons are closest to the nucleus. That's where the electron for hydrogen, at least, that's for where the electron for hydrogen starts. And so there's a certain quantity of energy associated with exciting that to n equals 2. If I have that quantity, it will be excited. If I have more energy, then I could potentially excite it to n equals 3 or even higher, to 4, 5, or 6, right? But the energy difference, say between 1 and 3, I can calculate the exact quantity of energy if I put in n equals 3 here and n equals 1 here. So I just put a 3 in, and that would be 3 squared. because of the squared there that's in the formula, and I put a 1 in for the other value for n. That tells me the energy associated. How do I know whether that energy, when I put it into that formula, is an energy absorbed or an energy emitted? Well, that depends on whether the electron is moving further away from the nucleus or whether it's already been excited and it's going to move closer to the nucleus. Right? So if I'm pushing it away to a higher potential energy, that requires the atom to absorb energy. Once it's already excited, all these transitions that have down arrows, these are the ones that involve energy being emitted. If it's already at a higher potential energy and it goes back down to a lower potential energy, that's when light is emitted. Okay? And so based on the quantity of light emitted, we can tell exactly how much energy is associated with each one of those energy levels, 1, 2, 3, 4, 5, 6, etc.